Okay, let's look at problem 5 from the exam. Boundary conditions. Okay, so we have u sub t equal alpha squared u sub xx minus v u, and that is for 0 less than x less than 1, t greater than 0. All right, well, so we've got both diffusivity and convection. And I think the key with trying to develop these boundary conditions is to look at extremes, okay? So, assume that v equals 0 first, okay? So in that case, all we have is diffusion. And if we have the diffusion, really what we would then have, it'd be kind of like a pond, but we just have a bath out there beyond the 0 and the 1. And that bath has particle amounts of 0. And so this is really a type 2 boundary condition for that. So, the boundary conditions on for type 2 would be that we would have u sub x equals some lambda and then just u, because it would be u minus 0. Okay, so this is the g of t being 0. And this would be at both ends. So really, I guess I should write, right, u sub x. Let's see. I got to look at something here real quick just to make sure I doing what I want to do. Let's see. Yeah, and that's where I thought that's what I wanted to do. Okay. So, yeah, let me just erase this one. I'll make that a G1 of t. So, I need it at both ends because it's going to change it a little bit, right? U sub x at 0 and t is going to be lambda u. At 0 and t. And I'll put a G1 here because G1 of t is 0, and similarly then u sub x at 1 and t, and that's what I was looking up to make sure I didn't get it wrong, was minus lambda u of 1 and t. But again, it's the bath is, I'm going to call it G0, and this one G1 is 0. Okay, so that's assuming no convection, right? We'd basically just have a pond, and we'd have these open boundaries where it's moving into a bath, and so and we would assume that the bath's big enough that it overall it stays at 0. Then let's assume alpha equals 0. Okay, what if there is no diffusion? Then what happens? Well, I'm going to sort of draw a funny picture of this, but here's 0, here's 1. right? We're starting out with something that looks kind of like that. And I'm going to write timelines here where time is going to move to the left. So here's sort of time 0, and then some time 1, don't know what the units are, some time 2, some time 3, some time 4. And these are actually, I'm just pushing this whole interval to the left, is one way to think about how I've drawn those timelines. So at time 4, really this hump is now centered over the x equals 1 spot. So sort of what's happening in that case, well, up here, we're going to have that that bath and flux, I guess, so up here, we're just going to see 0, right, under this condition. So, under this condition, u of x 0 t would just be 0 all the time. Okay, but notice here, we would definitely have some u sub x. And so now let's think about that, is that, let me write this way and use the chain rule. So this would be the partial with respect to t times the partial of t with respect to x. Well, it's not partial, sorry. That's a real live derivative. Okay, so we would have that, and the units would match and all that. And we sort of have that because that is just 1 over dx dt. So we got the partial of u, partial of t, times 1 over dx dt. But so now I'm going to write this as u sub t times, whoops, not v, but 1 over v. Okay, so we have that. And so under this assumption, we would have that our u sub x at 0 in t is equal to 0. And u sub x at 1 in t is equal to u sub t at 1 in t over v. So now putting those two things together, just adding them together. Oh, and you want to think about the sign here to make sure we have that right. So v is whatever it is, right? It's moving to the right. We probably call that positive. So as we look at u sub t here, if u sub t is negative, right? So it's, if it were going down, then u sub x should also be going down. And if u sub t is going up, then u sub x should also be going up. And that's kind of what I see here, right? Is that, if I move in time, right, I go from time 0 to here, and I look at the values, u sub t is increasing because u is getting bigger over time. But actually, yeah, now that we look at the picture, however, the derivative of u sub x is negative there. So really we need a minus on that. Okay, so now they are ready to go. And we'll add the two together. And so our boundary conditions are that u sub x and 0t are just what we had before, lambda u of 0 and t. But then at the other end, we get our minus lambda u of 0 and t. But then we also get a boost, at least in the same direction as the lambda. All right, we get a boost of u sub t, oops, that was a 1, of 1 and t over v. And this is for t greater than 0. Oops, greater than or equal to 0. And so that, we need to modify this right-hand boundary condition to take into account the convection. And so there we have it. That is our boundary condition for problem 5.